Hi everyone, welcome to my introduction to algorithm class. And today is our 10th lecture in the 5th week, which is the sorting number 4, analysis of the sorting algorithms in all the syllabus as you have gained. So welcome my student Ling Qiong and welcome my student Yanan. Okay, cool. So first, let me ask a question. So in the previous 3 lectures, we have covered most of the the typical algorithms in our class. So what algorithms can you remember? So Ling Qiong, name some of them.
Quick sort and
Quick sort.
merge sort.
Merge sort. Cool.
Double sort,
Double sort.
selection sort,
Good. Selection sort. Any other ones you can remember?
insertion,
Cool. Insertion sort.
And heap sort.
Heap sort, exactly. And in the and you just mentioned the 6 of the sorting algorithms. And in our last lecture, we also covered some linear time sorting algorithms. And in today's class, we are going to make comparisons among those typical sorting algorithms and to having you a better understanding of these algorithms and their time complexity analysis and the comparisons between these several algorithms. Cool. So first of all, let me write some name of the algorithms. So the first one we cover in this topic is the bubble sort. This marker is not good enough, but yeah, bubble sort. And actually, for each of these sorting algorithms, I'm going to write its time complexity. I will include their average time complexity, their best performance, and in the worst case, what will they perform? Cool. So Ling Qiong, so can you tell me what's the average time complexity for bubble sort?
I can't remember that.
You can remember?
Yeah.
Yeah. So, good point. Because this is the first sorting algorithm we have ever covered. So actually, I prepared a video for you. So let's look at this video on the TV. So this is a very fancy dancing video, so illustrating how bubble sort works. So let's take a look. It's very fancy. So in this video, people are weighing numbers in their clothes with numeric values. So let's see. So the first 2 people compare with each other, and then 3 is greater than 0. So the number 3 is coming from A0 to A1. Then 3 is compared with 1, while 3 is greater than 1. So they switch with each other, and then keep going on. Then 3 compared with 8. 8 is already greater than 3, so they keep their original positions and go on, right? So we call this algorithm bubble sort because it's like floating bubbles from the bottom of from the bottom to the top. Then after a pass, we see that the greatest number or the lightest bubble are actually keep floating from the bottom and up. So finally, let's see. After this switch, the number 8 coming from A2 to A7, then to A8. Then the final comparison is between 8 and 9. So while 8 is less than 9, so they will keep their original position here. Cool? So this is one pass. So for one pass, then another pass starts. So after each pass, there will be some numbers already sorted and they will turn around. Right? So in average, we will give n passes, and for each pass, they will switch something around n times. So the average time complexity will be order n squared, right? So these videos are available online, and I won't cover them all. So if you are interested, you can watch them on YouTube. So they're available. So can you tell me what's the average time complexity for bubble sort?
N squared?
Exactly, good point. Okay, so now we have order and square, and then we will also have in the worst case, so they will switch, over and over again. So in the worst case, the complexity will also be order and square. And in the best case, bubble sort. So in the best case, if in the past none of these dancers are switching with each other, that means this array is already sorted. Right.
Yeah.
In that case, it will stop immediately. So in the best case, the time complexity for bubble sort will be order n. Right. It will be order n. Very good. So this is bubble sort, the first algorithm we have covered in this class. And then after that, we also covered two more sorting algorithms. One of them is the selection sort. Selection sort. And another one is called the insertion sort. Cool. And so anyone can tell me what's the average time complexity for selection sort and insertion sort?
N square.
Cool. Which one?
Both of them.
Right, both of them. The average complexity is order n squared. Very good. And actually, these three algorithms are the typical, basic sorting algorithms with the average complexity of order n squared. And in the worst case, of course, they are also order n squared. Right, order n squared. So here's another problem: is that what's in the best situation? What's the time complexity for selection sort? So the point here is that what is selection sort, right? So what are the differences between selection sort but with bubble sort and insertion sort? So let's take an very easy example. So if the array to be like 3, 1, 4, 2, and we want to sort it, ascendingly. In bubble sort, the first comparison will be between 1 and 3. Then it switch to be 1, 3, 4, 2, and then the number 3 compared with 4. So keep the order, and then 4 is compared with 2, and they switch. So after the first pass of bubble sort, it will become something like this, and this one is sorted, right? This is bubble sort. Then let's see selection sort. In selection sort, the idea is that in each pass we pick the, we pick the smallest number in this array and put it in the first position, right? So in this one, in the first pass we check, is 3 the smallest number? Maybe. And then is 1? Yes, update. Is 4? No. Okay, 1, 2, no, 1. So after a pass, we know that the smallest number in this array is the number 1. So we put number 1 into the first position. Then switch 1 and 3. So after one pass, it becomes 1, 3, 4, 2. This is the pass. Then after a pass, we get the first one sorted. And then this keeps n times. So in that way, we can see that in the selection sort, actually, it's guaranteed that this algorithm won't finish before n passes. While in each pass, it will check whether, and find out the smallest number in the array. So in the best situation, the selection sort still needs order n squared time. Right, n squared time. Very good. And the third one we covered in the class is the insertion sort. In the insertion sort is actually trying to sort the subarray from the beginning. Let's still take this one as example. As example, we can see that. So in the first round, we only sort the first elements, then 3. Okay, it's sorted. And in the second pass, we sort the first 2 elements, and then so we insert the 1 into this array. That is 1 is less than 3, so we insert it before this one, so we get 1, 3. Right, so that is second pass. In the third pass, we insert 4 into this 1, 3, 4, so it becomes 1, 3, 4. And in the fourth pass, we insert 2 into this position, right? So it becomes 1, 2, 3, 4. So that's the insertion sort. So can anyone tell me in the best situation, what's the time complexity for insertion sort? This one is tricky actually. This one is tricky. So we see that the time complexity comes from two components. One is that how many passes, right? How many passes? And in each pass, how many how many switch or computations do we need? And according to the definition of insertion sort, we need to insert each of the elements into a previously already sorted array. So these passes will be a fixed number of n. And in the best case, we can use order 1 time to finish this insertion. Because in the best situation, if this array is already sorted, then we can use order 1 time to check that 4 is already greater than 3. So it will definitely be the last elements in the array. So we use 1 time to finish this insertion times n passes. So in the best case, this insertion sort complexity will be order n. Cool. Any questions so far?
No.
Cool. I see students are taking notes. Very good.